Hey guys, and welcome back to this episode of Curious Scientist. This video is an introduction to how the Lagrangian can be used as a tool in mechanics. So the Lagrangian, what is it? L equals T minus V, where T is the kinetic energy and V is the potential energy. Now what this means is that for any physics problem, you can simply write down the kinetic energy minus the potential energy, and then it is just mathematics until you can solve your problem. So this means that the hard bit in your equation is actually working out what the kinetic and potential energies are, rather than resolving forces like you might have to do if you were using Newton's second law. The second equation that is used with the Lagrangian method for mechanics is the Euler-Lagrange equation itself. I'll just write that down. d by dt of dl by dx dot equals dl by dx. Now I won't go into what this equation means for the moment, but it relies on something called the principle of least action. But what it can do is translate any Lagrange equation, so the kinetic energy minus the potential energy, into differential equations whose solutions are the solutions to the physics problem. Let's see if we can apply this to a problem of our own. What I've drawn here is a simple pendulum, the type that you will meet very early on when solving equations using Newtonian mechanics. But now let's see if we can solve it with the Lagrangian method. The first step then is to write down the kinetic energy in the system. T equals half mv squared, but here we want everything in terms of the one variable that we have in this problem, which is theta. So v is actually theta dot r. So v squared is theta dot squared r squared. Theta dot squared r squared. Likewise, we need to write down the potential energy. And in this system, the potential energy is equal to mgr times by 1 minus cos theta. Now you can see why this is true just by looking at the diagram. We can draw in another distance, h, which is equal to the vertical distance through which the pendulum has been raised. And h in this system is equal to r 1 minus cos theta. H equals r 1 minus cos theta. Since the potential energy is just mgh, we can then say that the potential energy is mgr 1 minus cos theta. And now this variable h is redundant because we have it in terms of cos theta, so we can go ahead and rub that out. Now, time to write down the Lagrangian in full. L equals half m theta dot squared r squared minus mgr 1 minus cos theta. Now we can apply the Euler-Lagrange equations themselves. First we write down dl by dx dot, and note that this is a partial derivative. So dl by dx dot is equal to m theta dot r squared. So d by dt of dl by dx dot is simply m theta double dot r squared. Next, we can say what dl by dx is, and again, this is a partial derivative. dl by dx equals minus mg sine theta. You just have to be quite careful with the minus signs here. So, now we know that these two terms must equal each other. M theta double dot r squared equals minus mg r sine theta. And with a little bit of algebra, we get that theta double dot equals minus g over r sine theta. Now, in its current form, this equation is actually unsolvable. This is the equation for large amplitude simple harmonic motion. So we have to use a small angle approximation. We have to say that for small values of theta, sine theta is approximately equal to theta. Sine theta is approximately equal to theta for small values of theta. And this gives us the following equation. Theta double dot equals minus g over r theta. And this equation is solvable. These are the equations for simple harmonic motion, and I'll just write a solution down now. Theta equals a cos omega t. If you have any questions, then please feel free to put them in the comments section below. You've been listening to a Curious Scientist video. If you liked it, don't forget to hit that subscribe button so that you can get new videos just like this every week.